Welcome to Quantum Computing Fundamentals. Uh, just wanted to check if it is recording. Yeah, it is recording. Okay, let me go back. So we are on this session number 6 of Quantum Computing Fundamentals, and this is July 3rd, uh, session number 6, part 1, Hilbert Space, Tensor Products and Multi-Qubits, which I'll cover from San Francisco here, and Gokhale is from almost close to North Pole, you can say. He's north of Helsinki, 200 kilometers north of Helsinki, and he'll be covering the part 2. So what we have till now is we have the whole course divided into 4 parts. The first part being the quantum fundamentals, which will be, this will be the last session, 6, which will cover all the fundamentals we needed. The part of it is more like a revision, but straightening the thing that if you do this, you will be able to go on to quantum circuits, and then the communication and the compute algorithm associated in the August-September timeframe. July, we should be able to close the quantum circuits. So 1 month, one area, that is the focus. Moving on to this week's, we are going to cover Hilbert space, tensor products, and multi-qubits. Of course, it is spread over many topics, subtopics, I would say. The reason is you have to merge all of them, like Hilbert space, then going with Hilbert space with tensor products, then with qubit, then Hilbert space with tensor products, then multiple multi-qubits, and then again the products. So it's a uh, convergence of all these things what we have done coming here in this session. And you can see the same thing will happen when Gokhale covers at a very, what do you call, uh, n dimension space and m dimension space. So I will let him handle that. Just focus on what I can do here. So we start with Hilbert space. So we should have done this in the beginning, but it is better that going through all the mathematics and complexities, we have come to a situation where we can understand the basic. So the basic is in quantum mechanics, which is the mother of quantum computing, the state of physical systems, which is represented by a vector in Hilbert space. So that means you have a vector which is representing the Hilbert space. Now, if you remember the first session when I said vector space is all encompassing. So everything is within vector space. Now, within that vector space, you can have a real and complex real number spaces or scalar spaces. Then the vector can also include specific variations like Hilbert space. Hilbert space can be for 1, 2, n number of electrons. So let's say for one electron, which is a spin up and spin down, we have a Hilbert space, which is a complex vector space. Why we are calling it complex is because it's not the simple position vector that you have a origin and you have a end termination of it and the length between that. So there is a position and angle, but besides that, this has some properties which are very typical only for Hilbert space, and that is that the inner scalar product or inner product of the complex vector space, this complex vector space has everything which is in the inner product of any vector for that matter. In that space, if you have one vector, you'll have you need two vectors to have inner product. That means what? It's a transformation of one vector to another vector, and when you do that, it rotates, and that is based on the inner product. So inner product is the key word. Hilbert space is a complex vector space with an inner product. So if you have one space, you have one inner product. If you have two space, you'll have two inner products. If three space, three. If you combine them, then the question comes how they are combined. And that is where there are various ways of combining those spaces. And superposition is what we would focus right now on. So we will now also say that Hilbert's space is actually supposed to be infinite dimensional of inner products. But at the same time, uh, to really have a, if you say infinite, then where do we end? There has to be some So what we do is we limit it to certain m or n and say that this is a uh, closed with n dimension or m dimension, and therefore this is a product of those inner products. That space is what is represented by this. So that is the Hilbert space. So we tend to make it more finite dimensional space, which automatically satisfies the condition of completeness, because completeness requires that everything is included. But what is everything? So we limit it. So that way we solve the problems of infinity, avoid that. Now we will use Dirac notation. We have read about it and we have used it. Like if we have a vector v with a bar and a v and a greater than symbol, we call it as ket. So we have a ket v. Same way we can have uh, a C, a complex number. Now complex number is ai plus bj or a plus ij or a plus some I number, that is imaginary number. So one real plus one imaginary or combination thereof. So that is the C, the complex number. Now when you multiply a complex number with a vector, which is ket v in this case, we are going to get CV. Now how you represent uh, is a question of whether we are using what do you call whether we are using ket or whether we are using standard arithmetic way of doing it. So let's get to 2. We have to talk about 2 because giving vector v and w, if you have 2, then only we can do a dot product. Otherwise, single vector, what do you do dot product? So we are doing v and w. Let's say we have 2 vectors v and w and we do a dot product. And the dot product is represented by bar with a bra v, that is the less than v symbol is the bra side of it with a common uh, what you call a straight line, and w similarly bar, and bar w greater than is the ket symbol. So you have got a bra and a ket. So when we multiply uh, vector ket v with vector w, then what happens is we have to take a uh, um, to be able to get the dot product, we'll have to take a complex conjugate of v, and therefore we represent that as bra v. So bra v ket w is the dot product of vw, two vectors. And what we have is that is, we can also say same thing vw like this. Instead of that, we can say, hey, I can use a complex conjugate of v directly into dot of uh, w. So basically these and these two are same representation. However, this is not the common one, this is the most common one. So bra v ket w is the bracket notation for Dirac for a dot product. So let's take a simple two-dimensional space, which is where every vector can be written as combination of two vectors as basis. So now why did we do this? This comes out of the notion, or when we say qubit, it means that it is a linear combination or superposition of states, basis state. So basis states are 0 and 1, and they are mutually exclusive. That means if I am finding that a state collapses, because state space represent the entire computational space for us. So on the computational basis, you have either a 0 or a 1, and we call that as ket 0 and ket 1. So ket 0 and ket 1 are themselves the vectors. Instead of VW, now we get into ket 0 and ket 1, the real ones which we use for measurements and all that. So let's say if we use the concept of ket 0 and ket 1, which are Z basis, because if we have a apparatus which we use to measure, and that has, let's say that be a magnetic bar, a north-south pole bar, with north facing north and south facing south in the vertical direction, then uh, that is what will measure. And so when you measure, and then if it is up, then we call it spin up. If it is down, then we call it. So basically, if you throw a stone into water, if it is heavier, then it will go down. Whereas if it is light, it will be up. It may not be a stone, it may be something wood, but all it means is if it floats, then it is has higher energy. If it goes down, then it is a lower energy. That's the interpretation of spin up and spin down. So that means a subatomic particle electron, if it is moving away from the uh, what you call the center of the atom, that means it is getting loosened, and that means it is getting out of the level and it is free to move around, and that is spin up, and when it is getting in, it is pinned down. So because they don't have a position which is fixed, they keep on all the time hovering around like a uh, what do you call, if you have a flower and you have a bee flirts around all around, so something similar it is. So in our subatomic particle representation, ket0 and ket1, on a computational basis we call them as two-dimensional ket0 ket1. And when we take a product, uh, obviously if you have a different, the definition of uh, dot product is, they, if if they are uh, exclusive, mutually exclusive, then it will turn out to be zero. But if they are in the same direction, or they are in the similar measurement direction, like if I have a zero which is ket zero and I have a bra zero, then they are nothing mathematical representation of the same direction or same spin, so which is spin up. So if the two of them are spinning up, then it is a 1. If one of them is mutually exclusive, then like 0, 1. Ket 0 and ket 1 are mutually exclusive, or bra 0 and ket 1 are exclusive, and therefore their product will be 0. Dot product will be 0. And we are only focused on dot products which have unitary value. If they are not, then it's irrelevant to us, or we can zero them out and say that we don't have any value for that. And the that means what, in terms of representation of WV, if we have WW or VV, that makes sense to us. WV, if they are different, like 0 and ket 0 and ket 1, they are 0. So basically they are orthonormal, and then you really can't do anything about it. They are mutually exclusive. Either you have this or that. That's the probability. Okay, let me go to continuing on Hilbert space now. uh, all the physical and interpretation I have given. Now let's go to rigorous mathematical. In rigorous mathematical terms, if you describe W, we will be also be using this E and F, E for electron vector and F for the second electron vector. So let's say if we have two E and F2 vectors, which we'll also probe in later in when Gokhale covers some of the portions. But here I am going to focus on the 5 necessary uh, conditions which a Hilbert space vector F and E will satisfy, or F and G will satisfy. You can do any of the E, F, G, H, whatever. But let's say in this case we have said F. So if you have a vector F, so the scalar inner product of two vector, if it is to itself, they are, that means what, F to F means what, inner product of vector itself is has to be positive or 0. So it should be greater than equal to 0. Why not 0? That's a big question. Because if you are 0, then it's not a vector. That's the problem we have. Because you have to have an endpoint starting from 0, and then it must go somewhere, right, in the space. So therefore, even if it is a virtual space, still there is a 0. And therefore, it's not 0, but greater than or equal to 0. That's an indication that the vector product of F with F itself is greater than 0. That is one condition. Second equation, if you look at, which is complex multiplied, a complex, so scalar, uh, complex, real, scalar is nothing but either a real or complex number. And so assume, say, if it is complex, then if you have two F and G as the two uh, vectors, and if you multiply ket F by ket G, then the scalar product of that, if you scale it with a complex number C, then if it is going to be taken C of Fg equal to C star, that is, you can have a complex conjugate multiplied by Fg. Or the other way around is, if you don't want that way, you want that F bra F is used. If you use bra F with ket G, then it is C into Fg. So basically, how you uh, juxtapose between C of Fg and F of Cg. So basically, which one comes first, which one comes later? How do you do the complex? Once it is CF is together, then this CF, if you do a bra to a ket, it will turn out to be, you have to have a T star, a G as it is. So basically, when you take this off from the vector, you have to complex conjugate it. Same way, if this was already in the bra space and you are taking off, then it becomes C. So basically, this 2 and 3 are equivalent of saying that you need complex conjugate or you don't need complex conjugate. Depends on how you are doing. Like example, in the 3, we are multiplying KTF as bra version on G, followed by complex conjugate. So basically, what it means is you are taking a ket G and you are having a F's bra. Therefore, you have a complex conjugate. But if you have, in the other case, what is happening is no complex conjugate is here, because the second, to scale the second vector, which only appears to be in ket space. So that means D is in ket space, so you are scaling it with C. There is no change in that. But in the case of F, it's a bra which you are multiplying with. So if you multiply ket with ket and ket with bra, there has to be a change. Otherwise, you leave it as it is. So it's bit what you call difficult to understand. But remember that when you change the ket to bra, bra to ket, you do a complex. Otherwise, you don't. Because this is C is part of the bra here, therefore you do a complex conjugate. Here C is part of the ket, so you don't do. That's simple. If you make that understanding, that will be easier. And obviously, we are considering that multiplication together as a single vector with a scalar multiplier. So that is the reason for this. Now, if you could go F and G, if I reverse the G in this case, okay, so here the G, that what you call bra, the greater than symbol is missing here. I'll correct that. But you can say ket F, bra F, ket G is equal to, if you invert it, then it will be GF, and then you have to do a complex conjugate of it. So this is fourth one is nothing but a it's a projection. So projecting G onto F gives a scalar which is a complex conjugate of the projection F. So that means, so when you do a projection of G on F versus F on G, it is going to be complex conjugate. That is what it requires, and that is what the Hilbert space will require and satisfy. So any vectors, most of the vectors which we choose unitary will satisfy that. So the last one is nothing, distributive law, A plus B into C is A, C plus BC, something in what we do in normal algebra, that will apply here. That means K of F plus H. Now this is one term and the other term is G, because your dot product space is F plus H. So when you say F plus H, we can split it into F into G and H into G. Basically, that's what we are doing in this case. And if we have understanding that, we have to remember that what is scalar out of it is important. What is vector? So F and G are vectors, and that's the reason for this. So what I'll say, when we say any vector in quantum Hilbert space, which is representing the spin or representing any phase, horizontal, what do you call, the polarization, vertical polarization, flux, charge, etc., whatever, plus minus charge. For any of those, if we represent them by a form of a vector, F and G, they will satisfy this condition, with the C being complex which is what the Hilbert space allows us to do. Yeah, it's a bit tricky, but the previous slide, if we had gone through what we have said, if you remember that orthonormal basis, they will be equal to 0 here, example. Non-orthonormal basis, there will be 1. So this 2 is the ultimate conclusion, and I will move on to expression of Hilbert space and tensor product. Now we saw Hilbert space of two linear combination of 0 and 1, because vector Hilbert space, when we talk of a vector, it's a linear combination of superposition of vector spaces. And vector spaces 0 and 1 is what we take as the state for, because any vector which is there in that space, if it has a transformation, rotation, and then it has to follow the dot inner product of dot of their states to be able to complete the requirements, fulfill the requirements which we had shown in 1.5 earlier. So we represent generally we represent a what you call a vector psi, ket psi, which is a combination of linear combination of ket0 and ket1 two vectors, which fulfills those requirements. Because we need two vectors and we have two vectors here, that is the ket0 and ket1, which is the linear combination, and that becomes the psi vector. So we have spin up and spin down as the two vectors, which is the combination superposition of the two, which helps us describe the single spin, single electron whose spin up and down we represent, and those fulfill those requirements. Now if you have spin space of Hilbert's space H1, one for electron spin, other for real position. Now there is no such thing. H1 is a virtual space, right? At the end of the day, it is virtual. So virtual in the space, it is hyper space, we call it. That means it is not, it's imaginary. So once it is imaginary, then you are looking at two, let's say we have one H1 space with one electron spin and another real, let's say real time. If it is a real position vector, which we describe position vector XYZ vector, if you have a position vector representation and we have a Hilbert space H1 representation, and we call the second one as, let's say, H2, we can combine the two to create a Hilbert space, which is third, which is called H3, which is a tensor product of 1 and 2. So here we have to remember that tensor products are little bit different than normal set theory which you use. So just to clarify, first thing is X with a circle, as you see here, this is called as vector product. And when you have F1 and H2 being G2, so H1 is formed by F1, let's say vector F1, H2 is formed by G2, then H3 is nothing but the ket F1 tensor product ket G2. So we'll be moving from C2 space to C2 to C2 square, which is C4 dimension. So if you have 2, you move from 2 dimension to 4 dimension, which is a H3 space. Now just to distinguish between the position vector which we studied as well as the Hilbert space we have introduced now. So you remember, in ordinary Cartesian space, we would get an m and n dimension as simple sets. So if I have an ordinary Cartesian coin head tail spin, then I have either a head or tail. And if I have a dice, then it can have 1, 2, 3, 4, 5, 6. So head tail we represent as 1, and the combination of the two produces how much Cartesian space, which is head tail 1, 2, 3, 4, 5, 6. So set of m plus n equal to 8. So you have m plus n plus n is equal to 8. The same thing if we say that I am going to use a Hilbert space for coin and dice permutation, then what will happen is it will be m into n. That means 2 into 6. That means 12 permutations are available. So tensor product is not limiting to Cartesian, which is only 8. In this case, the tensor product is not 8 but 12. So what it means is that there is a difference between Cartesian products, which is based on the set theory, versus the Hilbert space quantum mechanics or quantum information theory that is based on the tensor. Every operation, every operation in quantum space is a tensor product. Remember that. That will solve half the problem, because the confusion is because we are trying to imagine the quantum information uh, as a decimal representation or binary representation. But that's okay as far as trying to build a similar analogy. But beyond analogy, we have to be practical. What is the real meaning of the tensor product? So tensor product of two vectors, let's say if you have two vectors A and B and represented by AX circle B, which is nothing, tensor product of A and B. So if we have a tensor product of A and B, and there is a term C which is equal to the tensor product A and B is defined as CK. That is, we are calling a C a vector with a kth element on that. The kth element of that will be nothing but combination of I and j in terms of representation. That means the ith and jth, ith term of A and jth term of B, when you multiply, you will get Cij. And we have to imagine in this case that A and B are some kind of a column vectors to start with, which will be A0, A1, AN, depending on what is M for this. So it will be A0 to, if we are taking M by N, then A0 to AM, B0 to BN. So, or N minus 1. Basically, that means what? Here, we have to take the uh, I 2 to the power, basically. So if I to 0 to I to 2 m minus 1, 2 raised to m minus 1, and j to uh, 2 raised to n minus 1. And that's why this is a little bit complicated to view in terms of this IJK notation. We will have a better notation when we go into real detail. But you remember that the Cij equal to AIBJ, which is equal to CK. So K is nothing but ith row and the jth um, um, ith row and the kth column, which is meeting the two. That is the CJK element, or CK element, which is the Cij element. So vector denoting a pure quantum state is separable. And that means what? If we have a superposition, then they are easily separable, pure quantum. Okay. But if we have something entangled, then it's not the same thing. So what it means, as long as we are using a wave as a wave function or as a particle, then we can represent this with superposition. If it goes beyond superposition, it gets entangled, then we'll have to look at some other aspects which we'll see as we go further. So entanglement is ruled out in this case. They call it as entanglement is a Bell state. So if I look at this one, if you lay 6 into 12, where are the other four? If I represent these as your 12 state and 8 states, where are the other 4 states? They don't exist as far as we are concerned, but they are. If we are going to go by the quantum, then those 4 must be entangled. That's what we have to assume for the time being. But that's only a thinking imagination. But most important for us to is it's m into n and m plus n. There is a difference between Cartesian and Hilbert space. And simplest one I could throw in is the coin versus dice and coin plus dice. And that gives you a expression of Hilbert space and its tensor product. So let's go to now expression of Hilbert space and tensor products in a way which is what we start with. Let's say f prime. So if you have a, so why is this prime coming into picture? The prime comes into picture because every vector space is its own. They are independent. That means if I have one electron, that's one thing. If I do something operation on it, then it becomes a different operation. Then again I do another operation. So vector keeps rotating, and the space, the vector representation keeps changing. Because we studied last time unitary. unitary is respect to time. That means if you have a state of a unitary vector at 0 time, then that is u0. But at time t, it is ut, then it is different. So it is the dynamics, not the static. What is the dynamics? And dynamics have to be represented by having some notion. In this case, we call it as prime, first f1. So f prime is alpha 1 plus beta 1, right? Because now the ket0, ket1 are with respect to first. Then if I go to G2, then they are with respect to, there is G double prime, then they are with respect to ket double 0 and ket double 1. So here it is alpha 2, beta 2. So overall what it means is to describe the system of two electrons which have individual spins, we can use a tensor product H3. So right now we are talking of H1 and H2 as being two single spins, two electrons with single spin each having its own space, and we are merging those or combining those into a third space. So the third space, if you look at it, when it comes to third space, then there are four, because each one has one, right? This has a ket0 1, this has a ket0. So H1 has a ket0 1, H2 has a ket0 1. Now they are not the same. If we have to say, then we have to write down that one of them is combination of the other. So example, ket3, ket0 3 is combination of ket0 first ones and second ones, both 0 combination, and that is this combination. Same way, ket3 is combination of that H3 represents 3, H1 represents 1, H2 represents 2. So basically 0, ket0 in H1 space to ket0 in H2 space. If you do a tensor product of the two, you get the ket0 of the H3 space. And that applies to 0, 1, 2, 3. Yeah, we could have written 0, 0, 1, 1, all that, but it's simple decimal terms I am writing. It is easy to comprehend that we have got 0, 1, 2, 3 as the final states, which are combinations of the 0 of individual H1, H2 space, 0, 1, 1, 0, 1, 1 of the respective spaces to derive at the final space. And this now, remember, dropping out this tensor product is very normal. What it means is, if you don't write that, it means it is always a tensor product. So basically what we have eliminated this and say, oh, this is nothing but, and finally we'll even eliminate this prime and double prime and say, hey, they are in the 0 in the same direction in the z basis calculation. So they should be 0, 0, that will come to 1. If it is 1, 0 or 0, 1, they will turn to 0 and this 2 will turn out to be 1. And that's what ultimately will happen. And that's what is happening in the equation at the bottom. What you can see is, you can write H3 is alpha 3 ket0 plus 1 plus 1. So now what is happening is so this is the combination on the basis of 4 states, and each states has a alpha, beta, gamma, delta. So we call it as alpha 3, beta 3, gamma 3 and delta 3, and all of them are representing this. So our H3 space is nothing but these combined with alpha 3, beta 3, gamma 3 and delta 3. That's what it is doing. And that is for the H3, ket H3 is equal to combination of these 4. And so if we write in terms of vector, this is how we write. But if in terms of column matrix, if you want to write the H3 itself, then we'll represent a 4 by 1 column. This I'm writing as a row, but this is 4 by 1 column. That means alpha 3, beta 3, gamma 3, delta 3. That will be the 4, what you call the weightage. That is the coefficients. So representative of H3 will be those 4, alpha 3, beta 3, gamma 3, delta 3 in a column, 4 by 1 column. So basically Hilbert spaces, when we started, we had only 2, alpha 1, beta 1, alpha 2, beta 2, right? But when you come to 3, then you have alpha 3, beta 3, gamma 3, delta 3. So essentially, either we represent the matrix form, in column form, or we represent in kit notation form here. And either way, it will come out to the same thing. And this will be better understood when we go further. So let me go further. So we have taken 2 qubits. Now what about multi-qubits? So when we did for 1 qubit, we said psi equal to ket psi equal to alpha 0 plus beta 0, and then we combine them as one. When we had 2, then we say alpha beta gamma delta and then combine. Now instead of calling alpha beta gamma delta, if you have A0, A1, A2, A3, A4, A5, and so on and so forth. So we can go on this way n number. So that is what we want to present. But in this case, we are talking about a C2 space. T2, H2, we are interchanging, but at the same time, what we are saying is complex space is used for coefficients for the 2D complex vector. And when we have 2 qubits, we said it is C4, that is H3 equal to H1 into H2, which is 2 into 2, C2 into C2, C4. And that is because 2 to the power n will get into it. So if you have 4 dimension, then we have 2 C2 spaces. Similarly, if you have n dimension, how many it will be? Like example, simple, take 10 qubits. If you have 10 qubits, then how many dimension that will mean? It will mean you have got 2 to the power 10, because 2 to the power 2, 2 to the power 3, 2 to the power n minus 1, n, right? Either 2 to the power n you can put it, and depending on where we start, 0 to n minus 1, or we start from um, 1 to n. So 2, when you have 10 qubits, we will be talking of 2 to the power 10, and that means 10, 24 basis states. So the basis states which are there, because when we saw induction principle, we saw when you have 2, then it becomes 4. When you have 3, it will become 8. When you have 10, it will become 10, 24. So basically, on the basis of extrapolation or induction, principle of induction, we can say that when we deal with multiple qubits, we will be dealing with number of um, spaces, which will be 2 to the power n. So again, multiple qubits in a very, very simple terms. This is easy to grasp with all the imaginary thing I told you now. This is very simple, concrete. You have got number of basis vectors keep changing. If your number of basis vector is 2, then you get ket0, ket1, which is C2 space. If your number of qubits 2, then you got 4 bases, which is 0, 0, 0, 1, 1, 0, 1, 1. And remember, always MS bit to LS bit. That's something which we did not say earlier. So when we talk about bits, we always talk about 4-digit number, 4 bits, and the first bit is the MS bit, and the last bit is the lowest bit. That means what? 3210, right? Because 2 to the power 3, 2 to the power 2, 2 to the power 1, 2 to the power 0. That's we multiply to get the number in the binary bits. Same way here we have to understand that when we talk about 4 qubits, we are talking about 4 state basis vectors, and those, which one is MS bit? This is MS bit and this is LS bit. And when you do a cross product, the tensor product, you will get C2, C2 into 4. Same way 3, 8, and here we have written as binary 0, 0. Instead of that, to simplify the notation, we use decimal here. This is like a modular number. We say mod 2, mod 4, mod 7, mod 8. So this is mod 8 in with a 0 as the beginning. So 0, 1, 2, 3, 4, 5, 6, 7. Again, it will repeat 0, 1, 2, 3, 4, 5, 6, 0, 1, 2, 3. So this is like a mod 7, mod 8 with a 0 as the starting number. So in the case of binary, we have 0, 1, 0, 1. Everything has to be 0, 1, right? And same way here, everything has to be 0 to 7 for a number of basis vector being 8. And this is what C2, 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 it goes to C8 here, because you have got 3 of them. If you have n, then it goes to 2 to the power n, which is nothing but ket0 to 2 raised to n minus 1. So that is what it is. So ultimately, if you start from 0, you have 2 to the power n minus 1. So this you have to remember that 2 to the power n minus 1. There is a gap here. It is not 2 to the power n minus 1. So if I have 10, okay. So we have 2 to the power 10, which is 1024, minus 1, which is 1023. So it will be 0 to 1023. So I said 1024 here, right? Which means 0 to 1023. So 2 to the power n, after calculating that, you are subtracting 1. That's the, otherwise somebody will confuse 2 to the power n and then n minus 1, they'll say 10 minus 1, 2 to the power 9. No, not that. So make sure that you don't make that mistake. You first take the uh, what do you call exponent and then subtract 1 from the exponent calculation. So and also we have defined what is MSB and LSB. Those two are important factor, because when you do some circuit theory and all that, which we will do later from next, we'll have to start looking at, hey, which is the MS bit, and if you have a register of qubits, how do you represent them, which is the MS digit and what is the MS bit and LS bit, they will become very important. So therefore initially itself we are saying our left is always MS bit, and it's not like your Intel where low byte, high byte and low byte and high byte, they take it and they inverse it. So the computation wise, but most of the people follow the standard MS bit as the leftmost, and that's even starting from PDP-11 and even now to IBM Qiskit and all, where we will always take MS bit as the left side. And that I will just move on. Here we have nothing, but we are saying in the former case, the tensor product state due to electron A spinning off. So we are calling them as electron A and B and spin off it. And what we are saying is spin 0 A, spin 0 1 B. But then actually what we are turning out is, as long as you know that they are different, if they are in the 0, in this case what we are doing, 0 1A 1B equal to 0 and 1, we are removing the A B and then calling it as 1 in the later case. So what we are talking about in this case is about the MS bit and LS bit. Spin up and down uh, is a combination. I think this I need to be a little bit more careful. I'll come back on this later. I don't know what is written here. I can't interpret it now. Probably, yeah, I got it now. So 1 0. So 1 0, this is right. 0 1 2. So what it means, this 1 0 is representing 2 here, whereas here 0 1, which is nothing, this one is representing 1. So it's a matter of spin of A and spin of B bringing together as 0 1 and presenting as 1 here. So this is referring to 2, this being MS bit, this being the middle, and this being third, and this being the last least significant bit. So MS bit is this least significant, and in between is this 2 and 3. So 1 and 2, sorry, 0 1 2 3, 1 and 2. So this is nothing but a representation of tensor product, and we'll get into this in much better way when we get into actual calculation. So here is the tensor product, again repeating the same with F1 and G with a column vector. So we said alpha, beta, delta, gamma. Instead of that, we are calling alpha 3, beta 3, gamma 3, delta 3. It doesn't matter, those things are essentially the same thing. We did this with alpha, beta, gamma, delta here somewhere. Yeah, here we represented H3 here at the lower end. Instead of calling alpha 3, beta 3, delta 3, gamma 3, we are similarly representing here alpha 3, beta 3, gamma 3, delta 3 in a column vector. There I said COL col, which is equal to column. Now this can be taken as two spins of two electrons, alpha 1 and beta 1 and alpha 2, beta 2. And that is what is the representation here. As you can see, the notation here is a bit different because we are using Ket0, Ket1, Ket0's first electron, and Ket0 of second electron, and then taking a what do you call the tensor product of that, and then same way it goes on. This is actual multiplication, right? Because you are seeing that this whatever is represented here can be split into two parts, 0 1 0 1 0 and 1 1. So what it means is, have got the 1 2 1 2 1 2 1 2. That means first component of the H1, which is kit 0, kit 0. Then kit 1, kit 1. With the cross product with second electrons kit 2 and second electrons kit 2. Okay, so basically what you are saying is you are trying to have 1 1 with 2 and 2, and again 1 1 and 2 2. So basically you are this is what this representation is. So we can put it in a simpler term. You can do all this calculation. At the end of the day, we are going to get into a cross product. Sorry, not cross product. The tensor product. In this case, you can say alpha kit 1 beta. This one you can take alpha kit 0 1 plus beta 1 kit 1 into alpha 2 kit 0 2 and beta 2. So basically, we are separating the electrons now. Here it was all combined. Here we are separating them out. And when you separate it out, you will find that the terms which are going to be relevant are only which are of the same order. That means same, if it is kit, spin up, spin up, spin up, spin down, these will result in 0. Spin up, spin down will result in 0 because 1001 terms are nothing but they are mutually exclusive, mutually orthonormal basically. And if you are going to have orthonormal basis, their product will be 0. And so this will be 0, this will be 0, and we will turn out that even though we write down all this, but these two alpha 3 and delta 3 are going to be significant. These two will become 0 at some point of when we do the entire calculation. But in terms of representation, we'll have to include all of them. Alpha 3 is alpha 1, alpha 2, beta 3 is alpha 1, beta 2, gamma 3 is beta. So same thing, 0 0 0 1. Some people are very comfortable with 0 0 0 1 1 0 1 1. Some people are comfortable with alpha beta, whichever way you choose. But tensor products are nothing but combination of the products of the components. And in this case, the components are alpha 1, beta 1. And so this is Hilbert space 1, Hilbert space 2 combined to create a Hilbert space 3. It will have 4 states, basis states, and you can describe them as whatever you want. At this time, we are representing as alpha, beta, gamma, and delta, and alpha, beta for 2. So this is a tensor product. That this is nothing. This is repeated n number of time to ensure that you have understanding of it. And so this can also be done. This tensor product, when you do in Hilbert space, then that is what we have done already. And this can be done mathematically. And that mathematical tensor product is like an inner product. So what you do, you take alpha 1 and then the product with alpha 2, beta 2, take a beta 1, take alpha 2, beta 2. So this is like mathematical view of doing this. So take one component, multiply with 2 rows, second component multiply with 2, and put them in the first and second place, and then you get this all combination. The same thing we got there. See alpha 1, alpha 2, beta 1, alpha 1, beta 2. Same thing it is here. The same thing is being repeated here, but in a vector form, column vector form. So tensor products in Hilbert space are computed as column products. And the column products are not the way we think of matrix product, but they are in their own fashion. Just you take alpha 1, they use matrix, but at the column level, and here it is the representation. And this is for two spaces, and this is for two vectors, and this is for, they can be from L equal to 1 to J. So basically here we are taking J and L as the two suffixes, and then the suffixes, they are running from to N1 and N2. So you can have H1 with N spaces, n1 spaces, and G second one with n2 spaces. So you can combine and then you can get to the level uh, with different spaces. So essentially here you have F and G, here it is E and K, and when you combine F and E and J and K, then you get a F E and G K. So essentially the ket of this and the bra of this and a ket of this, and that is as is. So you can see that we are just removing that number and just saying that we are looking at this Fj and El in the dot product space or inner product space, and same way G and K we are looking at inner product space with, in this case, J running from 1 to n1 and L running. So this is, we are bringing the two summations together and just reshuffling this and removing the what do you call the, because we said that in quantum Hilbert space any tensor product symbol can be removed and then reshuffled in a way. So we are just saying that ket, we need a ket corresponding to ket, we need a bra, which is the bra we are putting together. So what we have done is, in this case, bra Fj with ket E we have combined, and ket Gj with bra KL we have combined, because this is a combination. Here you are dropping the two and just making this happen. So this is general Hilbert space equation, and we, it's like when you do a computation, you say 1 plus 2 equal to 3, a into b plus c is ab plus ac, something similar. That is the, this is quantum computing tensor product and in Hilbert space, where we can afford to drop these. So this is like, if you give some equation like this, you should be able to uh, arrive at this. So this is more like a mathematical, but tensor mathematics you can call it. So this is representation of tensor mathematics. It is complex, but nevertheless, as long as we are able to interpret, we are more happy than others. Is just a mathematical derivation. We can live with what is being presented here. So at this time, I should summarize by saying that for constructing higher dimensional Hilbert space, we need to use tensor products. And the procedure to produce these is simple: vector state in higher dimension. So if you have one spin, one electron and two spins, spin up, spin down, and that is it, it's a linear combination of two vectors to represent as a one superpositioned one electron with a up and down spin. And if you have two, then you present with four, and if you have n, then you represent 2 to the power n minus 1 as the number of basis vectors and corresponding representation to do the same. Now, can you do this in lower dimension and then make it work in higher dimension, or should you go and compute in the higher dimension? All that is possible. So either you do computation H1 and H2 and combine the two and then say this is what will happen in 3, or you take the two products, that is tensor product of 2, and then say, hey, this is what will happen in 3. This Professor Gokhale will show you in the coming further going down. He'll explain those. So at this time, I think I should come to a end on my side and hand over to Gokul. Sir, it's your floor now. I, I hope I
Thank you.
got
Yeah, thank you.
justified.
Yeah, thank you so much, Prakash. I was having some network issues, so that is the reason why I had to turn off my video.
Mm,
Apologies for that. Okay,
yeah, sorry.
so fine. So what I will be now doing is I will take this entire
Mhm,
discussion a little forward, and
mhm,
I'll be talking about generalizing this entire concept of evaluating a tensor product over higher order dimensions, right? With respect to quantum spaces, we more or less try to focus on typically a two-dimensional space. Here we talk in terms of setting it up into a generalized, wherein we talk about going up to infinity. But going up to infinity might not always be feasible, so we typically set up a upper limit after that. So we say that we will talk about generalizing this entire concept of evaluating and trying to identify operators, which are the tensor product operators, in the higher order spaces. So that is what we are going to discuss, and we'll also identify how I can specify these tensor products as operators. And there is a concept of what is called as partial measurement. We'll be discussing about that. And then towards the end, I'll summarize this entire thing by putting up a very simple matrix representation of this entire operations. Okay. So let me just get forward. Prakash, can I share my screen? Thank you so much. So let me share my screen. Give me a moment.
Yeah, I'm muting myself so that you will not have any.
Okay, fine. I just quickly confirm if you are able to see my screen. Uh, yeah, Prakash, can you see my screen? Just quick confirmation, please.
Yeah, I can see. Go ahead.
Thank you. Thank you so much. Okay. So, a very quick recap of what Prakash mentioned earlier is that we normally use the Dirac notation to represent the inner product of any two vectors, right? And we have got the vectors represented by their ket notation, like ket v and ket w. We write this as bravi ket w, which typically denotes the inner product, and this inner product is also just nothing but the dot product. And we have seen this. And how do we evaluate? We typically take the left hand side, typically the bra side, the bravi, create a complex conjugate of that, and then multiply with the right hand side. The right hand side happens to be the ket side. Okay. And what we will typically do is represent uh, any two vectors. We can call this as v and w vectors, and then we will extend this into n dimensions, and these n dimensions will be specified in the Hilbert space. And after that, we will understand the concept of the tensor products on these higher dimensions. We have already seen the tensor product of two qubits, and these operations are normally performed on the C2 space. The C2 space is typically the two-dimensional complex space, simply because our both the vectors were in the C2 space. So the first vector, let's say the G vector, was in the C2 space, and the H vector was in the C2 space. By multiplying that, we got a resultant, and the resultant will be in the C4 space, right? So what we will try to do now is just to see how to perform this tensor product from two vectors which are primarily multidimensional. For example, the first vector v could be of n dimensions and w could be of m dimensions, right? So obviously now we'll have to set up a mechanism so that the tensor product can be evaluated. So what I will also typically do is, let me quickly take you through this simple calculation of let's say the so-called tensor product on two vectors. As a small example, I'll just show it to you so that things will be pretty very clear. So permit me to share my screen, and I'm showing up out over here a simple whiteboard, and what I will do is I'll quickly set up my first vector. So let us say this first vector is having values, let's say 1, 2 and 3, and the second vector could be having some values out over here. These values are, let's say, 4 and 5, right? So this, the first vector is having 3 elements, the second vector is having 2 elements. So I can now just say this is of let's say these are currently real numbers, so I can normally talk this as R3 space, and this is also a set of real values, so I can just say these are values which are in the R2 space. Okay, so if these are complex, we call them as complex three-dimensional space or complex two-dimensional space. Now, the moment I talk about setting up this tensor product between the two, this is just nothing but realizing a column vector. So remember the tensor product always gives me a column vector, a vector rather. And what are the components? I will have to take 1 multiply with 4. Right? So it's a product of these inner elements 1 into 4. That's the first one. The second one will be 2 multiplied by 4. So the second element will be 2 multiplied by 4. The third one will be 3 multiplied by 4. Right? So it will be 3 multiplied by 4. And the fourth element will be 1 multiplied by 5. What is 5? 5 is the second element of the second vector. If I call these vectors as A and B. Now this A where tensor product with B will realize to me a resultant, let us say C. So this element of C will be nothing but 1 multiplied by 5. The next element will be 2 multiplied by 5, and the last element will be 3 multiplied by 5. So it is something quite similar to, let us say, taking a Cartesian combination of all the elements. And now what is the space out over here? This is once again R, but it's R6. Why did I get 6? It is a product of 3 multiplied by 2. Right? So this is one simple example. Let me take another example here just to give you an illustration of how this Cartesian product typically works. Let me take an example here of let's say 1, 2, 3, 4. Right? It's no longer now a column vector. It is now a 2 by 2 matrix. And then I will now try to evaluate the Cartesian product of this, or rather maybe the tensor product of this with respect to, let us say, some other values like 6, 7, 8, 9. Right? Now this gives me once again a matrix which is something like, let's say, a super matrix, and this super matrix looks something like this. The first element of this super matrix will be 1. This is 1 multiplied by this entire matrix. So 1 multiplied by 6, 7, 8, 9. Right? Similarly, the second element out over here will be 2 multiplied by 6, 7, 8, 9. Right? And similarly, you just get running through all the typical combinations. Then it will be 3 multiplied by this, 4 multiplied by this. And once you evaluate these multiplications, now you will just get all the inner terms. So this tensor product is very much similar to setting up a super matrix and then performing the multiplication, so that now you get typically the order of this will be, let's say, if at all I talk about 2 by 2 and 2 by 2, I'll be typically getting maybe a 4 cross 4 type of a matrix out over here. Just for illustration purposes, because this type of notations is something which we're going to use in a higher dimension. Okay, so coming back to the slides. Okay, so can we have a generalized representation of a tensor product? Which means what? If at all I want to specify this onto higher dimensional spaces, can I have a tensor product onto that sort of higher dimensional vector spaces as well? Now, these higher dimensional vector spaces are typically what are defined by the Hilbert space itself, right? The answer is yes. And how is it so? Remember, any vector can be represented as a linear combination of n basis vectors. A classic example is your Fourier combination. Any function can be represented as a linear combination of the so-called bunch of basis functions. The basis functions could be either exponentials, or basis functions could be sinusoids, right? So you can just express any function as a linear combination of these basis, let's say, basis function, the sinusoids or exponents. Quite similarly, we can always say that give me any vector v prime, and that vector v can be expressed as a linear combination in an n-dimensional space. So I have got this v expressed over maybe an n-dimensional space. Similarly, W is another vector having their individual components in an m-dimensional space. And now notice the fact that this E0, E1, E2, etc. up to En minus 1. What are these? These are the basis vectors in the first space. Similarly, F0, F1, Fm minus 1. So all these are once again the basis vectors in the W space, in the m-dimensional space. So you have got two separate spaces, and now you are having a bunch of basis vectors in their respective spaces, and using these we have defined these two vectors. Now the question is, how do I evaluate the tensor product in such a case? Now why do I require this? When you talk about my quantum representations, there could be typically two qubits, and each of the two qubit state could be identified and specified in its own space, right? So the first qubit's electron spin is defined in its space, and the second electron spin is defined in the second space. If at all I would like to understand the combined interactions between the two, the combined impact between the two, the combined interactions between the two, then I typically would like to identify whether I can have a combination, or typically evaluate some sort of a, let's say, projection of one on the other and vice versa, which all can be represented and evaluated using the tensor product notation. That is the reason why we are studying this. And incidentally, the tensor product will always give us an opportunity to examine the probability of finding the combination of these two qubits to be in a specific state, right? Quite similar to the way we said that the eigenvalue also gives us typically the probability of uh, estimating the state of a particular qubit to be either in the spin up or in the spin down state. Quite similar to that. So here we represent this in a bracket notation, and in the bracket notation we have got the first vector v. This is now the ket form, and that particular ket form will be like v is just nothing but a column vector of all these coefficient values. And notice the fact that this e naught hat, e1 hat, en minus 1 hat are the basis vectors. We know that. So this is a column vector representation of the first vector. Similarly, that is in the n-dimensional space. Similarly, w is denoted by these coefficients w0, w1, etc., wm minus 1. This once again are in the different space, the space for the second vector, and this is an m-dimension space. So this is an n-dimension space, this is an m-dimension space. N and m need not be once again the same. So please once again remember the fact that out over here, f0 hat, f1 hat, etc. up to fm minus 1 hat, these are just nothing but the basis vectors in the second space, right? So this is a bracket notation, and once I have got the bracket notation, I can evaluate the tensor product. So how do I evaluate the tensor product? The tensor product is denoted as the vector v tensor vector w, right? So vector v tensor vector w is, I take vector v, right, all these elements of vector v, and then I just say tensor on all the elements of vector w, right? And the moment I talk about expanding, then I will be getting v naught multiplied by w naught, then once again v naught multiplied by w1, v naught multiplied by w2, etc., etc. The entire series of combinations, and the final combination would be vn minus 1 multiplied by w m minus 1, right? So this is typically what I'm going to evaluate, exactly the same example which I showed you earlier on. Fine. So this is just nothing but the evaluation of my tensor product over these particular two vectors which are in higher dimensions, dimension n and dimension m. Now from this, let us understand how to represent this. If at all you look at this, the unit vector ei and fj, right? This is just nothing but the ket notation of ei and ket notation of fj, right? If at all I look at that, both these two put together is just nothing but the ket notation of ei, the unit vector, cross fj, right? So this also means the fact that these elements are once again just nothing but the compositions identified by the respective weights. Remember, these multiplications are the multiplication of the weights in terms of just nothing but the uh, vector space that is produced by the combination of these basis vectors. So what am I doing is something like this. Each of these, if you look at this, E naught, F naught, E naught, F1, etc., up to here, typically will give me all the permutations of the basis vectors from these two spaces. And those typically are used, and these coefficients will typically denote the weights. Okay, so I can now use the same concept and then I can represent this tensor product as follows. So I can just say the tensor product of V and W is just nothing but the coefficient. Just take up the coefficients V naught to Vn, and then tensor product W naught to Wm minus 1. As simple as that. So now what might happen is there are some cases wherein depending upon n and m, if you'd like to set it up into the same size, we just let's say if n is greater than n, some cases we also see the other elements to be initialized to zeros, but that does not really alter anything, excepting for the fact that the resultant you are going to get will always be m square, right? But there is an additional cost on computation. So if you understand this, then automatically now you know the fact that the resultant of this would be just nothing but a column vector which would be of size n into m. Okay, so if at all I have a tensor product, and if the tensor product is to be evaluated, I can also have a generalized representation for the calculation. So once again, I talk about V tensor product W, that is ket V tensor product ket W. I can write this as V naught, V1, V2, etc. up to Vn minus 1, and each of that typically multiplied with the W vector itself. So W naught, W1, etc. up to Wm minus 1, exactly like the way I showed you earlier on. And this further expansion will give you all the combinations of the products, and that is just once again nothing but a column vector of size n into m. Okay, so if at all you perform these operations in a matrix, so we can also represent this in the form of a matrix. So you can just say V cross n will be equal to V naught to Vn minus 1, and this W would be now a row matrix. So if you have a row matrix, then this will result to you in V naught, W naught, V naught, W1, etc. up to V naught Wm minus 1. That will be the first row. Similarly, with V1, you generate the second row, and so on and so forth. You can just once again denote and generate a matrix. So this sort of representation, the matrix representation, normally if we don't use it in quantum computation, it is good once again for generalization of this entire theoretical concept, and it is normally used in algebraic systems. Okay, so with that small caveat, let us move a little forward. So if at all I have vectors in n-dimensional Hilbert space, I can typically create a tensor product. Now, is it possible also to identify what are called as operators? And can I talk in terms of tensor product on operators? Remember, what is an operator? Operator is just performing some function on or some operation on a vector to result another vector. And normally this operator is defined in the form of a matrix, or it could be in the form of a vector, right? And if you talk about Hilbert space, every Hilbert space has its own operators. And what are these operators? These operators will perform some operations so as to change the state of the let us say the qubit. Okay, so if at all I consider, let's say, two electrons we can just say that both these electrons, each of them will have their own separate, let us say, space, and I can typically define separate operators in each of these particular space, and obviously each of these operator will be operating in the individual space of the electron that happens to be the C2 space. And if at all I have two electrons, obviously the combined impact could be studied in a C4 space. So what type of operators? uh, from physical example, we can say that I could have some sort of a magnetic field, and this particular magnetic field can be used to manipulate the spin of the electrons, right? So if at all I'm using this magnetic field to manipulate the spin of an electrons, and if at all I've got two electrons, obviously I require two separate magnetic fields, each one trying to operate on the individual electrons, right? So what does this also mean? Then I require two matrices, and each of these matrices will denote an operation, and that will be operating in their own space. And the moment I talk about two matrices defining two operators, automatically they will be working in those corresponding spaces, which also means the fact that both these two will be having their own basis vectors. Remember, every space will have its own basis vectors, right? So what I can typically think about is something like this. If at all I consider, let's say, two electrons as a complete system, then I can define a tensor product to construct the or define the state in a larger system. What is that larger system? A larger system is a system where you typically talk in terms of a four-dimensional system, maybe, or maybe it could be a C4 type of a space. So tensor operations typically allow, or tensor product allow you to create higher order spaces from lower order spaces. Uh, a little later on, we will also discuss this phenomena of trying to decompose a higher order tensor space as maybe a bunch of operations on lower order tensor spaces as well. So we'll just talk about both these two aspects a little later on. So here is a simple example of how I can create the tensor product of operator. Okay, so now we are talking about an operator. So let us say I have got two operators, u1 and u2, and both these two operators are in the C2 spaces, right? So these two spaces are separate spaces, so I can call them as space h1 and space h2. So h1 typically has the operator u1, h2 has an operator u2. And if I define the tensor product of h1 and h2, that gives me a enlarged space called as a h3 space, the Hilbert space, right? Hilbert space h3. Now, the moment I have the h3, is it possible for me to define an equivalent operator in h3 which is as good as the combination of u1 and u2? Okay, so let us try to understand this in a little more detail. So let us assume that u1 is a, b, c, d, right? So this is typically one operator. Similarly, u2 is yet another operator, e, f, g, h. So these are the two operators. Remember, once again, u1 is restricted to the h1 space, u2 is restricted to the h2 space. And I can now define an operator h3. Now this h3 is an operator in the h3 space, and I can define an operator in this h3 space, and let us say that operator is called as u. You can also call it as u3 maybe. Now I will just say u is just nothing but u1 tensor product with u2. So which means what? If at all I've got two operators in two different spaces, the tensor product of both these two operators gives me an operator which is also there in the Hilbert space H3, which is just nothing but the tensor product of both these two spaces. Remember, these two spaces are defined by their basis states. So how do I evaluate that? So I can just say U equals to U1 tensor U2. So U1 is ABCD tensored with EFGH. And the moment I do that, I get all these combinations, right? A multiplied by EGFH, C multiplied by EGFH, etc. And if I expand that, I will be getting this as AE, AG, CE, CG, etc. And this now would be the uh, complete operator, and this operator now would be operating on what? It will be now operating on the so-called basis states. So what are the basis states now? The basis states are now the what you call, I should say, the combined basis states of the C2 space for the first vector and C2 space of the second vector, right? So we know the spaces, let us say, are 0 1, they are ket 0 and ket 1. Similarly, for the second space, I will just denote this as ket 0 prime and ket 1 prime. So the prime which you see out over here typically denote the basis vectors in the second space, nothing more than that, right? So I now define this. These four rows typically now correspond to the four basis states: 0 0. So 0 state in the first space, 0 in the second space. Similarly, this corresponds to 0 in the first space and 1 in the second space. And this is 1 0 corresponding to 1 in the first space and 0 in the second space. And finally, this is the combined basis states 1 1. Right? So remember, this is just now my combined basis states. And what are these combined basis states? We started with the premise that we are talking about two electrons, and both these two electrons will have two basis states with the ket 0, ket 1 states. So this is what we mean to say. The first electron is always the leftmost, the most significant electron. The second one would be the least significant electron. So that is once again a simple notation. And this can also be denoted, let's say, in our normal decimal convention as state 0, state 1, state 2, and state 3. So once again, so talk about, let us say, two C2 spaces, and then you define the operators in those individual C2 spaces, and then you can realize an operator in the combined space, which is just nothing but a tensor product of these operators, and that will give you an operator which will be working in the C4 space. And what are the basis states for the C4? It will be state 0, state 1, state 2, and state 3. Okay. So what we can do is, let us take up a simple example of this. Let us say we have got in two electrons. Let us say both of them are currently having spin up. So because it is spin up, their vector notation will be 1 0 here as well as 1 0 here. So remember, this is the ket 0 for the first electron and ket 0 prime for the second electron, right? So what we can typically do is like this: just look at each of these electron separately, and then we can apply a operator in the respective C2 space, right? And if I typically do that, I can now talk about applying this, like U1, that is the first operator working on 0 will give me ABCD. That is, remember, that is my operator, and it is working on 1 0. This is my 1 0 ket 0, and that is just nothing but a b. It's in the ket notation, it is called as a ket 0 plus b ket 1. Similarly, if you take u2, u2 is defined by this operator here, and if this u2 is operating on let's say ket 0 prime, ket 0 prime is uh, the state 0 in the second space, so it is once again your 1 comma 1 column 1 0 as a column vector, and this will give me ef. And this ef once again in a bracket notation will be e, let's say 0 ket 0 prime plus f ket 1 prime. Okay, so remember, with this we can also evaluate this in the combined C4 space also, right? How do I do that in a combined C4 space? I will typically talk about evaluating this u1 0 and taking the tensor product of u2 0 prime. right? So u1 0 and u2 0 prime are already known here. So if at all I take this will be a uh, ket 0, b ket 1, and I take the tensor product with e ket 0 prime, f ket 0 prime, and just if you just juggle around, this is what you're typically going to get, and that will once again be the same representation like what we saw earlier on. So this same thing. So which also means the fact that whatever is you either take this entire operators, create the tensor product, create a bigger operator and then operate it, or you can also do them on individual accesses, and then something like superposition, you just combine them together and then you once again realize the same effect out over here. Okay, so yet another alternate approach is directly taking this value and then you can operate this on the tensor product directly of 0 and 0 prime. Right, so this is the third one. This is a direct approach. So you take 0 and 0 prime, take the tensor product of these two, and that will realize what is called as a ket for 0 0 prime. And ket 0 0 prime is once again you take the column vector for 0, column vector for 1, calculate the tensor here, and just expand that. You will get this resultant column as 1 0 0 0. And if at all you apply the same u to the 0 0, once again in the C4 space, this will be just nothing but this multiplied by 1 0 0 0, you will once again land up with the same value. Okay, so there are three different approaches, and all these approaches typically yield the similar type of a result. So if you expand this and define the so-called tensor product with respect to a comprehensive n cross m space, then you have typically a tensor product which is realized as an n-dimensional operator and an another m-dimensional operator, and that will give you an n cross m dimensional operator, right? So this is your n dimensional operator multiplied by m dimensional operator, rather not multiplied by, it is a tensor that is the same as evaluating this entire thing, and then you get typically all combinations and a huge super matrix of these values. Okay, so this is exactly what we spoke earlier on. So you can generalize this to any dimension. So what is exactly the fundamental concept that you need to understand is, I started off with let's say smaller dimensions, and the moment I evaluate this tensor product, I'm actually creating a larger dimensions and higher dimension space, and this higher dimension space normally increases exponentially. So 2 cross 2 I'll get 4 spaces, 4 cross 4 I'll get 16 spaces, 16. At the moment you talk about 16 spaces, obviously you are going to have 16 basis vectors. Okay, so similarly if at all you talk about confining every space to only a C2 space, and if this corresponds to let's say 1 qubit, by taking let's say 4 such qubits, typically you're going to get 2 raised to the power of 4, that is 16 typical dimensions, and you're going to also define 16 basis vectors, right? So the moment you have got 16 basis vectors, then the entire interactions can be represented as a linear combination of all these 16 basis vectors. We have this concept of what we call as a partial measurement. Okay, so one way to do a measurement probably is to measure let us say the entire state in one single go, like taking a snapshot. Okay, obviously when you take a snapshot, when you take a measurement, the system would typically collapse to whatever is a basis state. So if at all you have a system which is having two basis states, the moment you take a measurement, it will collapse to one of the two basis states. If at all you have got a system which has got four basis states, the system would collapse to one of these four basis states, right? Obviously, this will happen randomly. So when you talk about, let us say, considering the spins of these electrons, and if they are in the C4 space, the moment you talk about measurement at that particular point of time, randomly it would collapse to any one of the four basis states. What are the basis states? 0, 0 prime, 0, 1 prime, 1, 0 prime, 1, 1 prime. So it would typically collapse into any one of these 4 basis states. Now the question is, assuming that I have got some sort of a device which allows me to do this sort of a measurement without really getting into collapsing. That means what, I'm able to observe the current state. I can now say that for any vector, let us say we are considering the H3 space, and obviously H3 space is defined as a C4 space from H1 and H2. Then I would have these 4 basis states 0, 0, 0, 1, 1, 0, 1, 1 defined by their ket notations, and alpha 3, beta 3, gamma 3 and delta 3 typically would be the coefficients out there. And if at all we measure, let us say H3, the probability would typically collapse to any one of these 4 basis states, and the probability is given by alpha 3, the square, basically it is just nothing but the magnitude. Similarly, or beta 3 square or gamma 3 square or delta 3 square, any one of these. So if at all we identify that it is might collapse to 0, 0, then identify the fact that this would be the defining probability. Once again, it is random out over here. It does not necessarily mean that the moment I have got one eye of this, which is the highest of a probability, it does not guarantee that it is going to collapse to that. But these are basically the probabilities that tell me that it might collapse to any one of these 4 states. So I've got 4 probabilities for these 4 states to which it could collapse. Okay. So what is this partial measurement? Partial measurement is something like this. Let's say, getting back here, I need to observe and measure the state of both these 2 electrons. Suppose I observe and measure the state of the first electron and then identify the fact that this is a 0, which also now means the fact that the system could be observed to be either in 0, 0 or 0, 1 state. Definitely it will not be in 1, 0 or 1, 1 state. Which this also means the fact that the probability which would now have to be considered will be just nothing but alpha 3 q square or beta 3 square. Because I talk in terms of localizing the first observation to a 0. And the moment I talk about first observation to a 0, it would either collapse to 0, 0 or 0, 1. And because of that, the probabilities could be alpha 3 q square or beta 3 square. Okay, so just remember this. So what we typically say is something like this. I can use the projection operator to sort of identify what we call as a partial measurement. Now, what is this projection operation? Remember, we spoke about the projection operation also sometime earlier, wherein we said that if at all I have got one vector in one space and another vector in another space, using the projection operator, I can have, let's say, bra v1 projection ket v2. That will give me a mechanism and a scenario wherein the first vector first vector in the first space can be projected over onto the second space. Right? So this is what we have identified. So what we can typically do is something like this. Remember, here we are talking about 2 individual electrons, and each of these is having their own spaces. So I think it is a good option to use this concept of projection. So what I can typically do is something like this. If at all if I want to find out the probability of the entire system collapsing to 1, 0 state, then I can identify a projection operator, and that particular projection operator will be project for 1, 0. It is just nothing but let's say 10 bra and 10 ket, right? Actually, it is ket bra. Projection is, remember, it is always the ket followed by a bra. So it's 10 ket followed by 10 bra. So this is my projection operator. So if at all I take this projection operator and then try to work it out on maybe the space, the whatever is the H space, I can now define this as follows. So it will be alpha 3, right, beta 3, gamma 3, delta 3, working on, let us say, 10. This is my the so-called bra notation. Working on 10, the ket notation always comes on the left hand side, and working on once again my alpha 3, beta 3, gamma 3 and delta 3. And remember, when I take this side, what is that? That is typically my the so-called bra side. I will always have to consider the complex conjugates. I think Prakash sir has very clearly defined that also. So the moment I do that, this entire thing actually collapses down to just nothing but gamma 3, right? Why is it gamma 3? These values will now automatically turn out to be equal to zeros. So I'll be having gamma 3, which is 10 and 110, and multiplied by gamma 3, 10 on for the second part. And if at all you expand that, typically that will be gamma 3 conjugate multiplied by gamma 3, and that is in an absolute term, it will be gamma 3 square. So just notice this is my same denotation. The moment I talk in terms of 10, 0001, 1011, so the moment I talk in terms of 10, it automatically will map down to this gamma 3. Okay, so it's alpha, beta, gamma, delta, so it automatically boils down to my gamma 3. Okay, so which once again is consistent in the notation and in the computations as well. So in similarly, if at all I would like to find out if what exactly would be the probability of the system to collapse to either the state 00 or state 01, once again I can use the projection operator, and the projection operator now will operate on the operator will be 10 or 01. Let's say, remember, this is like 10, the ket 10, ket 1, 01. So these are the two different type of states, and that will give me this entire evaluation, which is 0000, the bra and the ket. That is my projection operator, and similarly that's working on either 00 state or your 01 state. So these for 00 and these for 01, and by the same type of analogy, this will be giving me a value alpha 3 square plus beta 3 square. Okay, fine. So typically you can also, it means what, using this simple example of a sort of a superposition, simply because systems are assumed to be linear. Hilbert space is a linear space. We can assume the fact that the observability of all the four states is there, but the measurements can now be also thought of as a superposition of the individual measurements. Okay, so this actually leads to the concept of what is called as a partial measurement. Okay, so what is this partial measurement? If an electron 1 collapses to, let's say, 0 during a measurement, then the probability typically is given by the probability to collapse to either 00 or 01. Right? Remember, the one of the electron is already, let's say, collapsing to 0, which also means the fact that for the entire system, the system will either collapse to the state 00 or 01, which also means that I'm definitely going to exclude this 10 and 11 state. And the moment I exclude that, automatically now the command probability will be given by alpha 3 square plus beta 3 square. Okay, this is just nothing but the same operation which we did earlier using the project operator. So this is my projection also. So with projection also, if we just apply like what we did earlier here, right, like here, it will once again yield the same result, alpha 3 square plus beta 3 square. So partial measurements can be done using projection as well. Uh, Coming down to the matrix form of a representation uh, in any type of a basis. So we already know one very, very simple fact. Give me a vector in one space. It is also very much possible for me to represent or denote that particular vector in a totally different space, right? Or initially we spoke about the fact that give me a vector in the context of a bunch of basis vectors. The same vector can be denoted in the context of another set of basis vectors. Remember now that another set of basis vectors typically would mean just nothing but another space. Right? Every space will have its own basis vectors. So here is a small picture. This particular picture is not really in the context of the spin mechanism. So this is something like a, diagrammatically some sort of a representation of space. So here, let us say I've got the vector v, and the vector v is denoted in this particular space, the ket0, ket1 space. And assuming that this particular vector v is a unit vector 1 out over here, obviously this means the fact that this angle would be, let us say, 45 degrees. And in that particular case, the denotation out over here would be 1 over root 2 ket0 plus 1 over root 2 ket1. We typically know that. So it is just nothing but 1 over root 2 1 in the 0 1 bias, right? So this is my 0 1 sorry 0 1 basis. So in the context of my 0 1 basis, I have this denoted as let's say 1 colon 1 comma 1 or 1 1 1 as a column vector. Imagine I have got another space, and that particular space is having its own basis, and let us say that is just nothing but a space where the space is denoted by the plus and the minus, where the plus is in line with the vector, and the moment that plus is in line with the vector, then obviously this same vector now is denoted as 0 1. So what does this mean? Basically, I've got the same vector which can be represented in two basis spaces, right, using two basis vectors, which also means the fact that if there is an operator which is defined in one space, is it possible for me to denote that operator also in another space in the context of other bases? The answer is yes. Okay, so here is a small example of representing the let's say an operator or even a system using the basis vector. So let us assume that I've got a basis vectors which is alpha k, where obviously now you're talking in terms of a generalization. The value of k could be in an n-dimensional space. This value will go from 0 to n minus 1. In a two-dimensional space, it will be 0 and 1. In an n-dimensional space, it will be 0, 1, 2, 3, 4, going all the way up to n minus 1. So that is basically your basis vectors. And the moment you talk about that, then your operator H, remember that operator H is now a matrix which will contain individual elements. These individual elements are typically scalar values, and I have these elements at positions I comma j. The ith row and jth column will define one of this particular element, and that particular element value is just nothing but alpha I h alpha j. So more specifically, it is the bra alpha I h ket alpha j. Now remember, now this h operator is working like as if it is a projection operation. Okay, so here is a small example just to demonstrate that. So we are going to use this rule. The moment you talk about expanding this, it just goes to a full page. But now that we have seen this earlier, I just denote it out over here, and this becomes a postulate. So let us take a small example out over here. Assuming that I've got two eigenvectors for a sigma z. Okay, now you know what is a sigma z space. And these eigenvectors are, let's say, alpha 0, alpha 1, denoted by their ket notations. And the vector representations are 1, 0, and 0, 1. And obviously, now this will be in a two-dimensional space, or it could be R2 space, right? Because currently these are real values. Now I can take this and identify a representation in the sigma x space. Okay, so is it possible for me to denote that? The answer is very much possible. So what we typically tend to do is we define this uh, matrix where the elements will be H00011011 because now it will be a 2 by 2 matrix. And for example, this H0 value would be alpha 0 sigma x. Sigma x is now my the original matrix representation of whatever is the operator, and multiplied by once again alpha 0, which is my ket. So it will be bra alpha 0 sigma x ket alpha 0. So this will define my H00. What about H01? That will be alpha 0 at sigma x alpha 1 out over here for the ket side. Okay, so this way I have all the 4 combinations. So let us quickly evaluate that here. So we know this sigma x is typically 0110, which is just nothing but the representation of sigma x, and we can find out what is this in the basis form for sigma z, right? So let us identify that. So for that, all we have to do is represent the sigma x and then represent this in the form of the computations like this. Remember, this is my computation. This is my formula for my computation. So my formula will be, let's say, bra alpha 0 sigma x ket alpha 0. So this will be bra alpha 0 sigma x ket alpha 1. This will be bra alpha 1 sigma x ket alpha 0, and once again here it will be both alpha 1 and alpha 1. So the moment we expand that, plug in out over here, this is what we are going to get. If we just quickly calculate, you're going to get this as 0 1 and 1 0. This is just nothing but the same thing. So that means what the system is, once again, this evaluation, this computation is consistent. That is something which we need to understand. Okay. So in summary, what we have done is we have seen a few tensor product operations on vectors and matrices. And the central concept and theme to understand is we can decompose a vector in a higher dimension space to a tensor product of two vectors in lower dimension space. Remember, this is something very, very important. It's a very, very powerful concept which we are going to use a little later on. Quite similar to saying the fact that if at all I have got two vectors in a lower dimension space, the tensor product will yield to me a vector in a higher dimension space, right? Secondly, when you talk about a partial measurement gives me the measurement in a subspace vector, right? Remember we had, let's say, a C4, and from C4, I'm now able to have a partial measurement that gives me a measurement in a subspace, which is a C2 space. And we can have these matrix representations, which allows me to transform these operators from one basis space to another basis space, or from one basis form to another basis forms. Okay, so that is in summary. Now there would be a collab. A collab will be uploaded. I want you to just quickly go through the collab and execute that collab exercises. Those exercises are what are mentioned in the book for your chapter 11 dot 1, chapter 11 dot 2, chapter 11 dot 3. These are three problems which are assigned in the book. So the collab that is going to be shared will be the small program snippets. I request you to run those and then check out their working behavior. Okay, we are going to have a quiz coming up pretty soon, and that particular quiz will be from basic or beginners, and we'll have something with respect to the intermediate as well as some advanced topics to be covered. The quiz will also be open to you. The notification to that effect will also be sent out to you very soon. So in the next session, the date would be announced. We are going to typically now talk about the second part. The second part is quantum computing and logic gates. So there's a small mistake out of here, typo. It has to be logic, computing logic and the gates. So we're going to talk about what is meant by quantum register. We're going to talk about quantum processing, entanglement, and the Bell states, the EPR paradox, and stuff like that. We're going to talk about these aspects as the first session of part 2. Okay, so quick references here once again from the book, and you very well know the book which we are following. And here is also another small, nice link, and I request you to just download this PDF, and that will give you enough information on the concepts which we are discussing. So, with this, I complete my session. Over to you, Prakash.
Thank you, Gokhale. It was excellent interpretation. At this stage, what I'll say is we will have uh, probably closure on this session and part one completion, and we will try to address in the what you call office hours on Wednesday, this Wednesday. We'll just make sure that we provide the links to everyone so that they can complete by next week. So if you are able to complete, because without completing this, our going to the part two will be a little bit of a shaky start. So we would rather have you all complete before we move on to the next part. So Wednesday we'll have a clear links established here, which we have not given you for some of the question and answers and all, which we quizzes and all that will ensure, and then we'll move on to the second. I think with this we should end the recording for this session. Hopefully, if you have any questions, you can ask in the coming open class in next few hours, maybe 6 hours, I believe, or no, 4 hours, for 3.5 4 hours, and we will try to answer all those. This is a recorded version, and this goes into the YouTube channel, which you can go over. While uh, going over it, you can ask questions when we come to the class today. With that, I will stop there.